Hello, everybody, and welcome to this week's workshop on the University of Ethereum. My name is Rachel Rose, and I'm your host today. Today, I'm joined with a very special guest, Matt Pagani. So he was actually my Solidity instructor back during the ENCODE Solidity ETH Denver Boot Camp, and is such an amazing educator, and I'm so honored to have him on for this workshop today. Today, we're going to be going over Blockchain 101, kind of as a primer to lead into Solidity 101, which we'll be doing on one of the upcoming workshops with Matt as well. So without further ado, Matt, I'll pass it off to you to do your introduction, and then we could dive into the presentation.
Hello, Rachel. Thanks for having me. Hello, everyone that's watching.
Absolutely.
It's a great pleasure to be here sharing a little about blockchain and about all of those terms that you see out there. I'm going to try and make them easy to get in the fundamentals and get you started as soon as possible in working with blockchain, working with smart contracts, and all that is involved with it. So let's begin. Sharing my screen here. I just have a few slides to go through, a few hundreds of them. Today's but an introduction to the subject. I'm going to try and make a mental map over some of the most important terms for us to pick today. But in the next series, I think on a next one already, we're going to get some hands-on, put our hands into developing smart contracts, putting our hands in doing those transactions that we're going to see today. Okay, but today is more like a subject introduction. That we have a big question. We jump to the content already. What is a blockchain in a very practical point of view? And then we're going to understand an iteration of that. What is Ethereum? How Ethereum works. And this big question, we see this word, all of that, but we never stop to think, what is a chain of blocks? What this actually means to the technical term? We often associate that with the products. We often associate that with the protocols that are out there. But let's understand a bit more on the concept of it. So, as a high-level abstraction, blockchain is a public database, somewhere that you keep data, somewhere that you keep records, okay, like a ledger, like a file, the storage system, something like this. You could relate this database term to anything that you have heard in the past of storage of data. So blockchain is an iteration of that. It's a public database that is updated and shared across many computers in a network. It is not centralized in one disk. It is not centralized in one location under the control of one person. No, it is a public database shared between many of the participants. We're going to see that it's not only distributed. We might see public databases that are distributed in many computers, but orchestrated by a single central party. No, blockchain, it is decentralized in that network. When we speak about block in the blockchain, we're going to say about the data and the state stored in those little pieces, little bits of storage units called blocks. This data and this state is pertaining to the balances, or you can say the ownership over the assets, over the tokens that are owned, that are represented inside this database. Okay, if I'm going too fast, let's just pick the thread here again. A public database, a place where we store information that we are going to slice this data in blocks. Each of those blocks are going to have a small amount of information, a small amount of the pertaining data there, of the state, of the balances, of the ownership. And whenever I update this state, whenever I send assets, whenever I change the ownership over those assets, I'm going to need a transaction. Okay, I cannot simply pick a value that was 1 and update it to 2? No. I'm going to need to do a transaction that is going to move assets from to, but we never have a single 1 point update. And this transaction needs to be added in a block. We cannot have a single transaction included in a network. I would need to pack them inside 2, 3 of them, 5 of them, 1 dozen of them, 100 of them inside a block. And then we submit this block to the network for this information to be updated. So if we have this public database where we have a lot of things stored, imagine a public database that is making a picture. We have a lot of pixels, okay? When we change something, we need to make a transaction. This pixel is coming from here and going to there. I cannot simply pick the pixel number 1 and paint it pink. You see? We need to have this structure of transactions. It's laying out the rules here. So the way that a blockchain organizes these blocks is to chain them one after the other. Each next block is cryptographically referenced by the parent and so forward until we can make all of the history of the blockchain chained together in one single flow of information. So this is a public database where all of the information is changed through transfers inside blocks, and each of those blocks are chained together. The previous one referenced by the next one, and so on, so on, so on. Everything that we have inside this data, every data that we have stored inside the state of the blockchain is a result of a chain of transactions that were computed since the first single block that was the Genesis block. And everything that we change would need the acknowledgement, we would need the agreement, the up thumb for everyone in the network, everyone participating in that network. If they don't agree, the information cannot be stored. Or in the worst case scenario, they would be stored in different chains. It would have a fork. Before we get to that, let's stop here on this idea that whenever we want to put an information inside this database, we need to make those transactions, and we need to include those transactions inside the block, and the block would need to be accepted by everyone. At its core, let's do this concept again. A blockchain is a replicated, deterministic state machine. Let's understand those 3 things. Whenever we say state machine, this piece of definition, let me go back one slide here. This piece of definition is a term that you can do for any algorithms, any explanation of systems that would transition between states in a discrete matter. You don't go from 0 to 0.5, 0.5 to 1. Would go directly from 0 to 1. You see, you have discrete places, just discrete states. You can call that a state machine. We can say that the blockchain is a replicated deterministic state machine because each of those blocks, each of those lists of transactions that are placed inside the blockchain, they produce a deterministic and replicated state. My balance is 1,000. My balance is 100. Everyone can agree with that. Transaction by transaction. Moment by moment, I'm going to have those updates. Let's see that in detail. Let's see that with an image later on. This concept, whenever we have this discrete difference between states, We don't have a gradual transaction from hot to cold, from 0 to 1, passing through all of the decimals. We would jump, we would teleport from one state to the other. We can call this a state machine. To better visualize it, this would be a state machine. Let's give a look at this flow chart. We have some sort of game here, and we have an initial state where the game is running. Okay. Whenever, for example, the player dies, we go directly to game over. We don't have a transition of 10 seconds for the game over to begin. Whenever the player clicks start, it loads. It could take a while for loading. When loading, we straight go into the game. And then we are playing the game. We click on the pause button. We don't have a slow down time until we pause and then nothing moves anymore. No, we straight go from the game running to paused state. And then when we click resume, it doesn't slowly start. It jumps directly for the game being running. Okay, so these are the same processes that happen when we send a transaction in the blockchain. It is either completely sent and included in the blockchain, or it is completely failed, or it did not exist yet. Another way to put it, it could be like a washing machine. So I could explain with games, or I could explain with washing machine. I gotta cover all the possible metaphors here. Because when you turn on a washing machine, you don't have a state where you are both cleaning and drying your clothes. You only start drying when your clothes finish the washing cycle, right? Otherwise, you are like dry cleaning. There are some process of dry cleaning, but it's not like this, right? And every time you have a state change, it's, for example, you put a white t-shirt with the red socks, and then boom, you have a state change. Now you have pink t-shirts, right? If you put bleach, or I don't know, I'm not a specialist. But this same thing could be used to explain how the blockchains work. Every time we do a transaction, something similar happens in that database. So each block added to the chain, remember, we don't add transactions to the chain. We add them in bundles. Like I sent $1 for you, you sent $1 to other person, then another person sent $2 for another, and then we pick all of these transactions and we put them in one block, and we include this whole block in the state at once. So if we have 100 transactions, before the block, everyone was with this state, with this amount of balances. After the block is included, everything changes at once inside the state of the blockchain. We don't have this soft transition, this gradual transition. So this updating the state block by block is 100% deterministic, is 100% result of the transactions included. So the state of the blockchain can always be defined by the genesis block and all the transactions after it. At any time, you can take a picture of a blockchain, pick all of the transactions, and calculate the current state. So you don't have any rooms for error, any rooms for counterfeit information there. Looking at a picture, imagine you have the block A, that would be the genesis block, where you have all of the balances, all of the ownerships of all of the things. And then at the block B, you would have a reference to the hash of block A plus a list of transactions. In the block C, I would have the reference for the block B plus a list of transactions there, and so forward. At any time, for example, I can look at the block D, pick all of the transactions from C, B, and A, and calculate the current state based in the genesis block and all of those transactions. So at the core, I could stop the recording now, for example. At the core, this is what makes the blockchain super secure. anything we build on top of that is going to be resistant by architecture, is going to be resistant by design over any kind of manipulation. It is going to be tamper proof. No one can come here and ask an information to change a past information, delete a record. Okay. Another thing that not only secure against manipulation of information, changing information, also the blockchain can be secure against censorship, against people taking this information down. Because every time that someone wants to put information in the blockchain, they would need to agree, they would need to form this kind of consensus, they would need to validate that the next block is valid. For someone to erase a past information or for someone to change a past information, they would need to convince everyone, or at least 50% plus one of the participants of the network, that this information is correct. This is not easy to do. And even if someone do, you would still have a fork, would still have a number of people that are following the correct information, that we could retake the operation of the blockchain at some point if needed. So there is no way for someone to break it all at once, shatter it all at once. The information, the working of the system, the processing of the data is distributed by nature, by everyone that is participating there. Block by block, the information being added is granted by this mechanism, and this gives at the core, at architecture level, all of the protections needed by the data in this blockchain. Every time they agree on the block being put to the blockchain, they end up agreeing with the state. They agree with the changes of the state, and thus indirectly they agree in the state that it's there. So you don't have people arguing about what is my balance, how much I own, how much I have inside of information inside the smart contract, whatever. Because if everyone agreed on the blocks that we're entering, no one can go there and say, hey, I don't agree with this state. It's impossible, because you gave thumbs up on all of the blocks that made that state possible at the first place. So if you have the blocks correct, the state must be correct, because the state is determined from the block, the genesis block, and all of the transactions. See? After you get those fundamentals, after you get those bases, everything that we hear about blockchain now starts to make much more sense. Oh, this is why it's impossible to hack. This is why it is impossible to tamper with the information, because of the architecture, because of the design of how a blockchain would work. Most of these complications that we are facing, the elliptic curve cryptography to create a public and pair, public-private key pair, or peer-to-peer networks that can connect to each other and solve latency problems. Now, all of these complications and complex terms that we find out there, we could abstract those and we could accept those features as given and not to worry about the underlying technology for now. If we focus just in the architecture, just in the states of things, I can make sure that at least the core, at least the basics of the blockchain you can get in those 40 minutes, 30 to 40 minutes of study before going for this new world of concepts out there. Eventually, you should learn all of these concepts if you want to become an expert. But for now, this could suffice. Okay, because you don't have to know, for example, if you have hosted cloud applications, you don't have to know how Amazon Web Services work before you host something there, before you use something there, right? Or if you did never deploy something to the cloud, but for example, have you ever sent an email? So Do you have to know how internet works to use it as a user, to understand how an email works, or what are the repercussions for the other part? You know that it could land in spam. You know that it could go for the wrong receiver, depending on how you configure. Okay, that is good. We can work with that. The same thing I'm trying to do today with those concepts about blockchain. You don't need to know the underlying tech for today, but you can move forward and understand, have a high level understanding of it. Okay, so let's get started with some of those fundamentals. First one, the transactions. Remember that I told that we don't insert the transactions directly in the blockchain. We put them inside blocks, and we put these blocks inside the blockchain inside the chain for it to become a blockchain and to have this state updated. So these transactions, these globally shared transactional database containing a lot of blocks that contains a lot of transactions. The information is there, is public, and anyone can read all the entries at any time just by participating in the network. Anyone can listen to this information. But if I want to change this data, if I want to submit a transaction, not saying of including the block in the blockchain for now. I'm just saying about submitting the transaction. I wanted to change my balance, for example. Can I change my balance? Well, if I can't, it's quite useless to have a representation of my balance, right? We are speaking about ownership over digital assets. And the definition of ownership is being able to spend it, being able to transact it, right? If I can't transact, I don't own it. If I can, I own it, right? This is the base most definition of ownership for digital assets. So if I wanted to change, if I want to use my ownership, how do I do that? So for that, I need to create this transaction. I have to sign a valid signature. We're going to see more of that later. We need to do a valid signature that anyone can accept, anyone can validate. And once this signature, this signed transaction is included, it is going to be applied as a whole. Inside a block, yes, but let's understand atomically in that transaction. When it's included, it's going to be applied as a whole. It is either completely applied or not done at all. I can't stop half of the way sending this transaction. I would either change all of the changes that I want to do or revert. Okay, this can be different when speaking about smart contract operations, but now we're speaking about, for example, native asset transactions, sending Bitcoin or sending Ethereum, those native tokens. So inside this ledger, some sort of table, Excel table that you have, something that has all of the balances of everyone. Anytime that I send some of this currency over, some of those assets over, another person should receive the same amount, right? I send $1, you should receive $1. If I send one apple, you should receive one apple. We don't want to send a banana and receive an orange in the other side. So this is the same thing with this transactional nature, this pairing of operations. Because if one side of the operation happens, for example, subtracting my balance, the other side is going to happen as well, adding the balance in the other account. If that wasn't true, if I send you 10 tokens, I could have those 10 tokens deducted from my account, but something happened in the middle, and then they are not added to your account. So I lost 10, you didn't gain anything, you gained zero. This can't happen in a blockchain. In a blockchain, every transaction makes sure that both operations succeeds or both fails. It's not possible to do this half, stop this in the half, okay? So if this transaction would have some problem adding this balance, that person is blacklisted, that person has the maximum balance, something like this. If I have some sort of problem when doing that on the other side, my balance wouldn't be affected as well. I would revert. This all would be undone at a whole. This would be what defines this transaction when it is included in a block. Before that transaction, you wouldn't have any of those state changes. After this transaction, you have all of the state changes. You don't have an in between. There is nothing happening in parallel. Okay, the blockchain always teleport the states forward. It never gradually changes. You wouldn't have concurrence. You wouldn't have anything happening in parallel here. And also, the safety of this transaction, that I can be sure that I signed it, is granted because this transaction is only going to be processed if anything of these conditions are not met. You would have the transaction failing. Even if, for example, if I have the 10 tokens to send, I'm trying to send 5 for someone that can receive, even if all of the financial part is correct, I still need to have the signature correct and all of the requirements. So the only way for including this transaction in the blockchain, even if all of the financials are correct, all the math is correct, is to be able to sign this transaction properly. To sign this transaction with a valid signature, that would be my signature, the signature of my address, of my wallet. And then if I did not leak the signature, of course, if someone has my signature, that would be understood by the network that I am signing. Okay. If I'm signing this signature, I'm saying that I'm going to spend this amount of my owned money or owned assets. This transaction will go through. We also have a very important requirement that we are going to see later, that all of those transactions need to be processed. They need to be worked by a computer. They need to be checked and stored. So then we need to pay the network with some gas tokens to pay those fees. So all of those conditions, they form those transaction requirements. If I don't match every single of them, the transaction would fail. If I don't have balance, the person can't receive, if the signature is wrong, if I'm missing gas. So all of these would make the transaction fail. It is only included in a block when I have everything working. Otherwise, I don't have any state changes from that. If we are saying, for example, an electronic currency, so I can simply check the signature to see if the person sending is the person owner of those tokens. And if the signature is incorrect, I can fail. I can say, hey, you're trying to rob someone else's money. So this makes it practically impossible to trick the network to believe that you are someone else, try and impersonate someone else, because those signatures are really, really, really big, and it's almost impossible to guess this signature by trying out like brute force or something like this. Due to the decentralized nature of the blockchain, you also need to compensate people for working for you. This is a very sensitive topic because a lot of people would desire the blockchains to run by subsidized money and all. But actually, for it to be decentralized, it needs to be self incentivize it. It needs to be self-sustained. Okay, I could even sponsor a transaction for someone else. Yes, but the blockchain should not rely on that. Because for the blockchain to be decentralized, you need to have incentives for each participant to work correctly toward processing those transactions and storing this data. So cost, this gas cost, for example, in Ethereum, would need to be paid. The signer, when signing the transaction, would agree to let go of the assets that the signer is sending, plus the transaction cost that is uh, related, that is a repercussion of that transaction being included in the blockchain. The same thing, because of the decentralized nature of the blockchain. You don't have like a central person to say what transaction came first or what transaction came last, what is the top priority, least priority. You have just a decentralized network of people trying to converge, people trying to have consensus. Because of that, you could uh, have if, for example, try to include 1,000 transactions at the same time in a decentralized network. What came first, what came last, who is paying more, who is paying less, it's almost impossible. So to mitigate this sort of crazy scenario, you would include those transactions in batches inside blocks. So the order of the transactions inside the block, and if a transaction is going to be included or not in a block, is completely defined by those incentives that we put when signing those transactions, when making those transactions to uh, designing those transactions to happen inside the blockchain. We don't have a way to guarantee that the transaction is going to be included in the next block. The transaction could take a few minutes, even a few hours to be included in the next block, to be included in the blockchain, because of how this decentralization happened. There are more people paying for the same space inside the block. If they are paying more than you, or if they are better connected, internet connection, some sort, with the nodes, you could expect their transactions to be included first. Okay, this could happen. This is how transactions work inside the blockchain. And also, that is the same structure for guaranteeing the correct order of blocks. Here we are now understanding the blocks part, because this chain of blocks is also the same way that the transaction need to be included in a block for being included in the blockchain. This order of blocks, this chain of blocks, is also part of the consensus. So trying to make a 2, 3, 4 payments with the same transaction could be possible if you tamper with the organization of these blocks. You can submit one block saying that you paid $1 million to this person, and then you submit another block saying that you paid $1 million to that other person, and then you do that 3, 4 times, and you could have these blocks in parallel, trying to do some sort of double spend. And you could say, okay, but that's easy to verify, right? If I try to spend the same money 10 times, 20 times, dozens of times, or whatever, I could just see the first transaction, make that first transaction work, and delete all of the other transactions or make them all invalid. Okay, but how to define what is first? We don't have, just told that we don't have a single central entity placing timestamps on transactions or blocks. We could have different nodes in the network to receive an information first, and the other would receive this same information later. Imagine like the sunrise. It takes 24 hours for everyone to see the sunrise in the globe. Sometimes more, sometimes less, depending on where you are, right? But this information could take a while to propagate. Even in the internet, even at speed of light, we would still have these latencies happening here or there. So for this double spend part, you as a user, you don't care. There is going to be a consensus mechanism in place in each of the blockchains that you are using that would solve that for you. You would have those transactions being bundled within those blocks. They would all be shared between those participants, those nodes in the network. And if two transactions contradict each other, the one that is being included in the blockchain later, even if it was sent first, even if it was sent 1 hour first, the one that is included later gets rejected. So I could send one transaction now, another transaction in 1 hour, another transaction in 2 hours, and the last transaction that I sent could be included first. That could happen if I'm trying a double spend attack, not normal transactions, see? And then that is all good. The problem is solved. No one is believing that I can spend the same on 2-3 blocks. But there is a thing. We do have a linear sequence of those blocks. We do have a linear sequence of those blocks where we have this word blockchain. But the tip of the blockchain, the last blocks added, could change. There are different blockchains, some different order selection mechanisms, some sort of mining or validation mechanisms that would be able to reorganize, to change the order on those blocks time to time. The further down in the blockchain you are, the less likely this is to happen. The more in the surface, the more in the tip, more often this could happen. So this creates another concept called finality. Okay, it is not just because the information was added in the blockchain that it's correct. It could still be a double spend attack. Could still be wrong information of some sort based in the transactions on the mempool, on the shared between the nodes. The more blocks are added on top of a particular transaction, of a particular block that has that transaction, the less likely is that this transaction is going to be reverted. So you would you would expect a delay of a few minutes, a few blocks, in some blockchains, a few hours or more, until you can consider a block final. There is no 100% finality. Even the block number one could change, but the amount of money or the amount of resources needed for that is tremendous. So usually, different blockchains have different parameters, but usually whenever you wait for 3 or 4 blocks in Bitcoin blockchain, or if you wait like 10 to 20 blocks in Ethereum blockchain, that is good enough for you to know that you have finality, that you can trust that information. Okay, so I spoke on a few examples about that. Let me see, I guess I have 6 minutes or so to go through some of the concepts here. But long story short, Ethereum is an implementation of blockchain where you have a proof of stake based consensus mechanisms that whomever wants to add a new block to this chain, whenever a person wants to do this process here I was mentioning a while ago, I want to be a validator in the Ethereum blockchain. Okay, I would need to stake at least 32 ETH, the Ethereum's network token, in a deposit contract and run a validator software for it to be for you to be participating, for it to be providing computational services for the network. Okay, because in the base layer, this is what uh, block being producing is you are providing computational services being paid, being rewarded, and you also put a stake there that so if you make bad decisions, you can be slashed. Okay, so this is the design of the proof of stake consensus of Ethereum. Anyone willing to participate to play this game need to stake at least 32 ETH to become a validator. And then they can be randomly selected on each epoch. They can be randomly ordered to propose blocks that all the validators can check before adding to the blockchain. That would be the specific implementation of blockchain for Ethereum. This design, usually you have just one canonical chain, one big chain, and eventually at the tip, like I mentioned, it's possible you could have multiple blocks being proposed at the same time due to latency or dishonest behaviors between participants. You could have fault, okay? But then the fork choice algorithm, the validators would participate to run this fork choice algorithm to select the canonical set of blocks. This would be by computing the votes, the endorsements, by the amount of ETH staked. So even if you happen to have the majority of the stakers in number voting for one chain, but you have one very rich person, very that staked a lot of ETH, very heavy on the chain, you would favor in the amount of ETH voted. Okay, so it is possible to manipulate in some sort by saying that hey, this block is correct, that other is not. Yes, but it would require so much ETH at the end that it's make almost impractical to change anything of value in the Ethereum blockchain. Okay, with a big risk of your money being slashed, being taken away from you if the network sees that you are making some bad decisions there. Okay, so this system of reward and penalties, it is what keeps the Ethereum blockchain in place. It is what makes Ethereum able to implement a working and stable version of a blockchain, different from what Bitcoin blockchain do, for example. So you have this native currency called ETH that behaves like a middleman, behaves like a venue, behaves like not a bad middleman, you see, behaves like a channel for people to negotiate, for people to participate in that market for computation. You wouldn't buy the computation directly with dollars, directly with euros. You would need to buy ETH first and then use ETH to pay for those transactions, to attract those validators, to incentive or even penalize the correct behaviors inside the network. Okay, so whenever you are using a little bit of block space inside the Ethereum network, you need to pay that using ETH instead of paying with other tokens, with other. You don't use a credit card, for example, for doing this transaction. The more we would desire that, but it needs to be this way for it to work. And then anyone participating in the network, anyone that would broadcast a transaction request, will need to offer some amount of ETH, some amount to pay the gas cost, for example, in Ethereum, for paying this transaction. We covered this back there. When you are committing this transaction in the blockchain, you would need to pay this little fee together with it for it to be included. Okay. So to summarize, ETH would be used for paying those transactions, for voting on those new blocks, for validators to wait, to have stake, to wait on in the decisions, and everyone that would pay those transactions fees. At the end, this amount of value would be transferred from whomever is paying to whomever is processing this transaction, the other side. So it also forms a sort of currency for paying for services, for computational services inside the Ethereum network. So this explains briefly what are blockchains, what Ethereum do. As a next step reading, I would suggest you to read about smart contracts. Those are special kind of accounts that we can have in the Ethereum ecosystem that they can host code, and these accounts they can be interacted. The normal accounts are the one that I mentioned, that we have this public and private key pair, but the smart contract account are the ones that can have code inside them, and then you can do some sort of computations over the transactions inside the EVM to produce cool things like games, like voting, like governance, like on-chain marketplaces, DeFi, and all of the cool stuff that we read about in the blockchain. This is all with this step, with this smart contract, that I suggest that you study this as a next step. Because we run out of time for today. So if you have questions, don't hesitate to reach us on our Telegram channel on V Miner Academy, that stands for Venture Miner Academy. And we're going to find a lot of all the students there, a lot of partners. I'm going to be there answering your questions as well. And I hope that you have enjoyed this lesson.
Awesome. Thank you so much, Matt. That was such an informative workshop. That was probably one of the most relevant workshops to what we're doing here at the University of Ethereum. Starting with blockchain fundamentals is so important before diving in and, building on top of these skills. So I will only leave you with one question today that I'd like to ask for our students and listeners. What are common pitfalls that people make when you see them coming in to work on blockchain? What mistakes or common pitfalls have you seen that students can avoid with the knowledge here?
Okay, yeah, a lot of people. This is why I love this kind of education, because a lot of people want to use blockchain before understanding what it is. Because a lot of things that we use are quite obvious and intuitive. We're using internet to connect to each other. Okay, we're using cars to drive around. Okay, all of those things are very intuitive. But blockchain at the essence is not a way for us to create fancy Ponzi schemes or meme coins or whatever. Actually, blockchain is something that can give you ownership over your data. And this is not evident. This is not in the surface. So a big mistake that people would do in the ecosystem is picking just the hot topics that are there, the launches, and try to use those Web3 technologies before understanding 1 hour, half an hour, what a blockchain is and what a blockchain can do for you.
Well, Matt, you've spent many hours of your life teaching people these things. So I think you are somebody in the space that has a very thorough understanding. And, thank God for people like you that show up in the space and have done all these different boot camps and cohorts. And we're so honored to be working with you. You've done really amazing work in our space. And yeah, this is just the beginning, you guys. You'll definitely be seeing Matt again here. We'll be going over Solidity next. So if any of you want to brush up on how you can use Solidity and start writing smart contracts, I've taken one of Matt's cohorts with the Solidity ETH Denver Bootcamp, which was really incredible. So you definitely don't want to miss this upcoming workshop. We hope you enjoyed this workshop today. And one last question for you, Matheus. I'm curious, what are your words of wisdom or advice that you would give to students or people just getting involved in the blockchain space?
The first things that come to my mind is try things, break things, see how they work. This is the only way to, in fact, learn what blockchain is. Not just don't just read out there. Apply yourself, try and put that in practice, and you're going to learn much, much more.
So essentially, don't be all theory and no action. Go out there, get your hands dirty, and try actually using the things that we're talking about here today.
Yeah, don't trust, verify. See if the things are the way that people are telling you.
Absolutely. Well, Matt, thank you so much for showing up today. We really appreciate you coming on to the University of Ethereum, and really excited to go deeper into Solidity in our next workshop. And for everyone that tuned in this week, thanks so much. Okay, bye everyone.
Bye-bye.